From an engineering perspective, roads are never just paths drawn across the landscape. They are systems. A functional road must solve several problems at the same time. It must support weight, resist erosion, manage water, maintain direction, and remain usable over long periods. If even one of these elements fails, the entire structure begins to degrade, sometimes very quickly. Because of this, roads tend to reveal more about a society's technical capabilities and priorities than many of its monuments. This is why certain ancient roads continue to raise difficult questions. Not because ancient societies built roads. That part is expected. Human communities have always created paths and routes. The difficulty lies in how many of these roads were built, where they were built, and how long they have endured. Across different parts of the world, archaeologists and engineers have identified ancient road systems that display a level of precision, durability, and large-scale planning that appears disproportionate to the tools and methods officially attributed to their builders. In some regions, these roads remain clearly visible on the surface. In others, they survive as structural layers beneath modern highways, cities, and rural routes. Their presence is not debated. Their age is not disputed. The civilizations responsible for them are well documented. And yet, when examined closely, the physical characteristics of these roads often feel difficult to reconcile with simplified explanations. This creates a technical question rather than a historical one. How did pre-industrial societies solve complex engineering problems on a large scale using tools and methods that, at least on the surface, appear extremely limited? Historians generally agree on the foundational framework. These roads were built by known civilizations, within accepted historical timelines, using human labor. There is no credible evidence of powered machinery, modern engines, advanced surveying instruments, or technologies that fall outside the established archaeological record. The builders relied on stone tools, early metal implements in some regions, wooden devices, ropes, levers, and organized workforces. These facts are not controversial. However, from an engineering perspective, accepting these facts does not automatically explain the outcomes we observe. Effort alone does not guarantee precision. Time alone does not produce consistency. And large labor forces do not automatically result in technically optimized solutions. To understand why ancient roads are so puzzling, it is necessary to begin with what is officially known, and then examine where that knowledge begins to feel incomplete. Some of the most extensively studied ancient roads come from the Roman world. Roman roads extended across Europe, North Africa, and parts of the Middle East, forming a network that supported military movement, trade, communication, and administration for centuries. Most of these roads were constructed between the 3rd century BCE and the 4th century CE, and their routes are well documented through archaeological surveys, historical texts, and physical remains. Excavations show that Roman roads were not simple stone tracks worn into the ground by repeated use. They were deliberately engineered structures. Builders typically excavated the soil down to a stable layer, compacted a foundation, added layers of crushed stone or gravel, and placed fitted paving stones on top. Many roads were slightly elevated in the center, allowing rainwater to drain toward the sides, reducing surface damage. From a purely descriptive standpoint, this explanation seems sufficient. The Romans were organized, disciplined, and capable of mobilizing large numbers of workers. Over time, such methods could produce impressive results. But when engineers analyze Roman roads in detail, additional questions begin to emerge. The first relates to standardization. Across vast distances, Roman roads often maintain remarkably consistent widths. Construction techniques repeat with striking regularity. Foundation depths, stone sizes, and surface treatments follow recognizable patterns across regions separated by hundreds or even thousands of kilometers. This level of uniformity suggests more than local improvisation. It implies shared standards, common training, and centralized oversight. Maintaining standard dimensions over long distances is not trivial. Even small measurement errors accumulate quickly when repeated over kilometers. Modern engineers rely on precise surveying instruments, reference systems, and mathematical models to manage this process. Roman builders did not possess these tools in their modern form. Yet the physical evidence suggests that whatever methods they used were reliable enough to produce consistent results across an entire empire. This introduces a logistical problem. If roads were built independently by local groups using informal techniques, variation would be expected. Differences in width, alignment, and construction quality would naturally appear. But in many cases, such variation is minimal. This implies coordination, quality control, and enforcement of standards. From what we know, this would require training systems, supervision, and administrative structures capable of operating across large territories. In other words, it suggests organized engineering practice rather than isolated construction efforts. And this is only one part of the puzzle. Another major issue becomes apparent when considering how these roads were used. Many ancient roads were not designed solely for foot traffic. Roman roads, in particular, supported wheeled vehicles carrying heavy loads over long distances. Military equipment, stone blocks, food supplies, and administrative goods moved across the network year-round. This placed enormous stress on road surfaces. From an engineering standpoint, heavy transport introduces several challenges. Without proper load distribution, roads deform under repeated use. Without durable materials, surfaces crack and disintegrate. Without stable foundations, structural failure becomes inevitable. Modern road engineering addresses these problems through layered construction, material science, and careful control of subgrade conditions. Interestingly, many ancient roads appear to follow similar principles, even though the language and tools used to describe them were different. Roman roadbeds often consist of multiple layers designed to distribute weight and absorb stress. This allows the surface to flex slightly rather than crack, a principle still central to modern pavement engineering. The longevity of these roads suggests that this approach was not accidental but intentional. The effectiveness of these designs is not in question. Many Roman roads remained usable for centuries, long after the political structures that built them had collapsed. The question is how such systems were implemented so consistently across such a vast geographic area. Consistency requires knowledge transfer. Knowledge transfer requires institutions. Institutions require administration. This suggests that ancient engineering was not merely practical or reactive, but systematic. The same pattern appears outside the Roman world. In South America, the Incan road system presents a different but equally challenging set of questions. Developed primarily between the 13th and 16th centuries, this network connected an empire that stretched across mountains, deserts, forests, and high-altitude plateaus. The roads included stone pavements, stairways carved directly into slopes, retaining walls, drainage channels, and suspension bridges. What makes the Incan roads particularly puzzling is the context in which they were built. According to the historical record, the Incas did not use wheeled vehicles. They lacked iron tools. They had no written language in the conventional sense. And yet, their road system spans tens of thousands of kilometers and crosses some of the most challenging terrain on Earth. From an engineering perspective, this creates a contradiction. Why build such technically demanding infrastructure if the society did not rely on wheeled transport? Roads of this quality suggest anticipated heavy use, long-term planning, and a clear understanding of terrain and materials. Once again, official explanations emphasize organization, labor, and time. Large, coordinated workforces under centralized authority could achieve impressive results, especially when working incrementally over decades. These explanations are not unreasonable, but they do not fully address the technical details observed in the field. Because effort alone does not explain controlled gradients, it does not explain consistent alignment across extreme terrain. And it does not explain why drainage systems in some areas still function centuries later. From an engineering perspective, one of the most destructive forces acting on roads is water. Poor drainage can destroy even the strongest structure in a short time. Many ancient roads, however, show careful attention to water management. Slight slopes shed rainwater. Side channels divert runoff. Elevated sections protect against flooding. These features are subtle but critical, and they point toward understanding rather than accident. Drainage systems only work if they are maintained. Channels must be cleared. Damage must be repaired. Otherwise, water exploits weaknesses and expands them over time. This brings us to another often overlooked aspect of ancient road systems: maintenance. Building a road is a finite effort. Maintaining it is a continuous process. Ancient roads that survived for centuries did so because they were cared for. Stones were replaced. Surfaces were repaired. Drainage features were maintained. This implies planning, resource allocation, and administrative oversight over long periods. In modern terms, this would be described as infrastructure management. From what we know, many ancient civilizations possessed administrative systems capable of organizing labor and resources. However, the scale implied by these road networks suggests a level of long-term coordination that is often underestimated. And this leads to another question that remains open. Why invest so heavily in durability? Modern infrastructure is often built with an expected lifespan measured in decades. Ancient roads, by contrast, appear to have been built with no clearly defined endpoint. They were not designed to be temporary solutions. This suggests a different philosophy. Perhaps roads were not viewed as projects, but as permanent frameworks upon which society itself depended. Once built, they structured movement, trade, communication, and control for generations. But even this idea leaves unresolved issues, which become increasingly difficult to ignore as the evidence accumulates. And those issues lead directly into the next stage of the problem. As the evidence accumulates, the focus begins to shift away from simple questions of construction and toward deeper questions of intent. Once it becomes clear that many ancient roads were deliberately engineered rather than casually formed, the next logical step is to ask why certain choices were made, especially when those choices appear to increase difficulty rather than reduce it. One of the most persistent characteristics of ancient road systems is their apparent disregard for what modern planners would consider the easiest route. In many cases, ancient roads cut directly across hills instead of winding around them. They maintain straight alignments even when the terrain becomes uneven. They cross challenging landscapes where alternative paths seem readily available. From an engineering perspective, this behavior is counterintuitive. Curved routes typically reduce construction effort. They follow natural contours, minimize excavation, and allow gradients to adjust gradually. Straight routes, by contrast, increase labor requirements. They demand more precise planning, more material, and tighter control over slope and alignment. Errors become more costly, not less, and yet straightness appears again and again. Roman roads in Britain provide a clear example. Many of them run in remarkably straight lines for kilometers, cutting across rolling hills rather than adapting to the terrain. From above, they appear almost indifferent to the landscape. This is not an illusion created by later mapping. Excavations confirm that the original alignments were intentionally straight. This raises a technical question. Why prioritize straightness when it increases construction difficulty? One possible explanation is navigation. Straight roads reduce ambiguity. They simplify orientation and make travel more predictable, especially over long distances. In a military or administrative context, this reliability could outweigh the increased effort required during construction. But navigation alone does not explain everything. Straight roads are only useful if their gradients remain manageable. Excessive slopes make transport inefficient or even impossible, particularly for wheeled vehicles and heavy loads. Maintaining workable gradients over long distances requires careful planning and accurate assessment of elevation changes. Modern engineers rely on precise elevation measurements, topographic maps, and computational models to manage this. Ancient builders did not have access to such tools in their modern form. Yet many ancient roads maintain slopes that remain usable even today. This suggests that ancient engineers had practical methods for controlling gradients, even if those methods were not formally documented. Sightlines, reference points, incremental construction, and constant correction could, over time, produce surprisingly accurate results. But accuracy on this scale requires repetition, shared standards, and feedback mechanisms. Once again, the evidence points toward systems rather than isolated effort. The same pattern appears when examining roads built in more extreme environments. In the Andes, the Incan road system traverses some of the most challenging terrain on Earth. High-altitude passes, steep cliffs, deep valleys, and unstable slopes are common features of the landscape. And yet, the roads remain remarkably consistent in width and function. Stone stairways are carved directly into slopes where wheeled transport would be impossible. Retaining walls stabilize paths along cliffs. In some areas, roads are elevated to avoid flooding or erosion. In others, drainage channels divert water away from the surface. From an engineering perspective, these features are not decorative. They are solutions to specific problems. The absence of wheeled vehicles in Incan society makes this even more puzzling. Roads of this quality suggest anticipation of heavy use and long-term reliance. They imply planning far beyond short-term needs. This creates another uncomfortable question. If these roads were not built for wheeled transport, what demands justified such a high level of engineering investment? One possible answer is logistical integration. Even without wheeled vehicles, moving goods, people, and information efficiently across an empire requires reliable routes. Human porters, pack animals, and relay systems all benefit from stable, predictable paths. But this explanation still leaves technical details unexplained. Consistency across tens of thousands of kilometers suggests shared knowledge and enforced standards. It suggests that builders in distant regions followed similar rules, used similar measurements, and solved similar problems in comparable ways. This would require more than local tradition. It would require institutional memory. Another major issue emerges when considering durability. Ancient roads were not simply built and abandoned. Many of them remained functional for centuries. Some continued to be used long after the civilizations that built them had declined or disappeared. Durability on this scale does not happen by accident. From an engineering standpoint, durability depends on material choice, construction quality, environmental adaptation, and maintenance. Weakness in any one of these areas can dramatically shorten a structure's lifespan. Ancient road builders appear to have understood this. Material selection was often adapted to local conditions. Stone types were chosen for strength and availability. Foundations were prepared carefully. Surfaces were designed to shed water rather than trap it. Water management in particular plays a critical role. Water is one of the most destructive forces acting on infrastructure. It weakens foundations, erodes surfaces, and amplifies freeze-thaw cycles. Even modern roads fail quickly when drainage is poorly designed. Many ancient roads, however, show subtle but effective drainage solutions. Slight cambering allows rainwater to run off the surface. Side ditches channel water away from the roadbed. Raised sections protect against flooding. These features require foresight. Drainage systems only work if they are designed before problems occur. Retrofitting drainage after damage begins is far less effective. This implies that ancient builders were thinking beyond initial construction. They were anticipating failure modes. And anticipating failure modes is a hallmark of engineering thinking. Maintenance reinforces this point. Ancient roads that survived for long periods did so because they were maintained. Stones were replaced when damaged. Drainage channels were cleared. Surfaces were repaired before minor problems became structural failures. Maintenance requires planning. Planning requires resources. Resources require administration. This suggests that ancient road networks were not passive achievements. They were active systems managed over time. In modern terms, this would be described as infrastructure governance. From what we know, many ancient civilizations had administrative systems capable of organizing labor, collecting resources, and enforcing rules. However, the scale and longevity implied by these road networks suggest a level of continuity that is often underestimated. This raises another question. Why commit to such long-term maintenance? Modern infrastructure projects are often constrained by budgets, political cycles, and short-term planning horizons. Ancient roads, by contrast, appear to have been built with no clear endpoint in mind. They were not designed to be temporary. This suggests a different way of thinking about infrastructure. Perhaps roads were viewed not as projects, but as foundational elements of society. Once established, they structured movement, trade, communication, and control for generations. But even this interpretation leaves unresolved issues. Some ancient roads follow routes that appear inefficient or unnecessarily difficult. They cross challenging terrain where alternative paths seem possible. They prioritize straightness and consistency over ease of construction. From an engineering perspective, such choices only make sense if reliability, predictability, or authority mattered more than minimizing effort. This introduces an important shift in perspective. Ancient road builders may not have been optimizing for speed of construction. They may have been optimizing for reliability over time. And that distinction matters, because it reframes ancient engineering not as primitive problem-solving, but as long-term systems design. As these questions accumulate, one thing becomes clear. The mystery of ancient roads does not lie in a single missing technique or unknown tool. It lies in the combination of precision, durability, scale, and intent. And that combination leads directly to the final stage of the problem. How do we explain these achievements without overstating what we know? That question remains open. And it is precisely where the final part of this investigation must begin. At this point, the problem of ancient roads can no longer be treated as a collection of isolated curiosities. The pattern is too consistent, and the scale too large. When roads demonstrate precision, durability, and standardization across vast regions and long periods of time, the question shifts from whether these achievements are impressive to how they were made possible within the constraints of their historical context. From an engineering perspective, the most important shift is this. The issue is not construction alone, but planning over time. Any society can build something impressive once. What separates advanced infrastructure from isolated achievement is repeatability. Roads must be built not once but many times by different crews, in different regions, under different environmental conditions, while still adhering to shared standards. This requires more than skill. It requires systems. Ancient road networks suggest the existence of shared technical knowledge that extended beyond individual builders. Measurements, construction methods, acceptable tolerances, and maintenance practices appear to have been understood well enough to be replicated across generations. This kind of continuity does not depend on innovation alone. It depends on institutional memory. In modern engineering, this role is filled by documentation, training, and professional standards. In ancient societies, the mechanisms were different, but the function appears similar. Knowledge was transmitted through apprenticeship, centralized oversight, and repeated practice. Mistakes were corrected, methods were refined, Over time, standards emerged. This helps explain how certain technical solutions could become widespread without formal written manuals. Practical engineering knowledge does not always survive as text. It survives as procedure. But even this explanation leaves open an important question. Why were these procedures applied with such consistency to roads, specifically? Roads require enormous investment. They consume labor, materials, and time without producing immediate tangible goods. Their value lies in what they enable: movement, communication, trade, and control. This suggests that ancient societies viewed roads not as optional improvements, but as foundational infrastructure. From this perspective, the emphasis on durability becomes easier to understand. If a road is expected to support an empire, it cannot be temporary. If it is meant to link distant regions reliably, it must withstand weather, use, and time. Short-term solutions would fail too quickly to justify their cost. This may explain why ancient roads often appear overbuilt by modern standards: layers that exceed minimum requirements, drainage features that anticipate rare but destructive conditions, alignments that prioritize long-term reliability over ease of construction. In modern engineering, similar decisions are sometimes made for critical infrastructure such as dams, bridges, or major transportation corridors. These projects accept higher initial cost in exchange for reduced risk and longer service life. Ancient roads may have been treated in a similar way. However, this still does not fully resolve the question of scale. Building one durable road is difficult. Building thousands of kilometers of them across varied terrain requires sustained coordination. Labor must be organized, materials must be sourced, work must be scheduled, maintenance must be planned. This implies administrative capacity. Ancient civilizations are often described as lacking the bureaucratic complexity of modern states. But this description can be misleading. Bureaucracy does not require paper files or digital records. It requires rules, authority, and enforcement. Road systems imply all three. Labor had to be assigned and supervised. Standards had to be enforced. Resources had to be allocated over long periods. This suggests that ancient road networks were supported by governance structures capable of long-term planning. From an engineering perspective, this is one of the most significant implications. It suggests that technical sophistication cannot be separated from social organization. The roads themselves may be physical evidence of administrative systems that no longer survive in visible form. Another key aspect of the problem is time. Many ancient roads were not built all at once. Evidence suggests that some networks expanded gradually, with segments added, reinforced, or modified over centuries. This incremental process allows for refinement. Early mistakes can be corrected. Successful techniques can be repeated. Over time, the final result may appear more advanced than any single generation could have achieved on its own. This gradual accumulation of knowledge helps explain why some ancient roads appear to solve problems that were not formally understood in theoretical terms. Engineering does not always require explicit scientific models. Empirical observation, repeated experimentation, and correction can produce effective solutions. This is especially true in societies where knowledge is transmitted through practice rather than text. However, even gradual development does not eliminate all uncertainty. Some aspects of ancient roads still resist easy explanation. For example, the degree of alignment accuracy observed in certain long-distance routes remains difficult to account for using simple sighting techniques alone. Small errors in direction accumulate quickly over distance, yet many roads maintain stable orientation across challenging terrain. Similarly, the control of gradients over long distances raises questions about how elevation was assessed and managed consistently. While incremental construction can reduce error, it does not fully eliminate it. These observations do not invalidate known explanations, but they do suggest that ancient builders may have possessed practical methods that are not fully documented or understood today. It is important to emphasize what this does not mean. It does not mean that ancient societies had access to unknown technologies. It does not mean that established history is fundamentally wrong. It does not mean that extraordinary explanations are required. What it does mean is that our understanding is incomplete. And incompleteness is not a failure of knowledge. It is a normal condition of historical inquiry. From an analytical standpoint, the most responsible position is to acknowledge what can be explained, identify what cannot yet be fully accounted for, and avoid forcing conclusions where evidence is insufficient. This approach applies especially well to ancient roads. The physical evidence tells us that these roads were built by human societies using available materials within known historical periods. It also tells us that the results were highly effective, durable, and systematically organized. What it does not fully tell us is how certain practical challenges were solved so consistently across such large scales with such limited documentation. That gap invites further study rather than speculation. It encourages collaboration between historians, archaeologists, and engineers. Each discipline brings a different perspective. Historians provide context, archaeologists provide physical evidence, engineers analyze performance and feasibility. When these perspectives are combined, the picture becomes clearer but not complete. And perhaps that is the most important point. Ancient roads do not demand that we rewrite history. They demand that we refine it. They remind us that technological capability is not measured solely by tools, but by organization, priorities, and long-term thinking. They show that societies can solve complex problems without formal theory, through experience and systematization. They also challenge modern assumptions. In an era where infrastructure is often built quickly, replaced frequently, and planned around short-term constraints, ancient roads present a different model. One that prioritizes durability, reliability, and continuity. This does not make ancient societies superior, it makes them different. And understanding those differences helps clarify the real lesson of ancient roads. The mystery is not that they exist. The mystery is that we often underestimate what human societies can achieve when they commit to long-term solutions. We may not fully understand how these roads were built, but ignoring the engineering questions they raise might be the real mystery.